Hello, this is Mr. Gilmore with the 10.8 regular polygon area lesson. Now, we have discovered the area for several other polygons. We've seen that now for squares and rectangles, parallelograms, triangles, even some other quadrilaterals such as the trapezoids, kites, and rhombuses. And now we're approaching our last set of polygons, which are the regular polygons. Now, we can really do without a formula. However, to foreshadow our next lesson on circle area, it's going to be helpful for us to actually have the area formula derived for that of a regular polygon. So where we begin is just reviewing some of the properties that we've can prove to be true about any regular polygon. So we've already seen this information before. This was information that we saw in the previous lesson, 10.7. But let's go ahead and remind ourselves of this because there are going to be some certain properties of the regular polygon that we're going to need to help us in our derivation of the formula. So first things first, there is a center. The center does exist, and this center point is the point such that it is equidistant from all of the vertices of the regular polygon. And so we see down in our diagram, point C represents that center, and as we denote there that each of those segments are marked as equal because that center, again, is equidistant from all the vertices. And remember that we give those segments names. The single segment we call there is a circumradius, or all of them together is a circumradii. We also have our apothem, which that apothem actually is going to be a needed value for us to calculate the area of a regular polygon. The apothem is that segment such that it's produced from the center of our regular polygon perpendicular to a given side. And what we saw in our last lesson is that the circumradius and the apothem come with a couple properties. So the two apothem properties are such that all the apothems produced in any given regular polygon are equal in length, and the apothems are bisectors. They actually bisect their corresponding side that they intersect. Our circumradius also has a property such that they are angle bisectors. So produce any circumradius to a corresponding vertex, and it's going to bisect that vertex angle there that's formed. And so we're going to find that it's going to be necessary for us to use some of these properties to help us derive the area formula for a regular polygon, but also in the practical sense, when we are looking for the area of a regular polygon, we're going to find that some of these properties are going to be helpful even after our derivation is found in approaching finding missing values that we're going to need to calculate the area. So let's dive into then deriving an area formula for a regular polygon. We're going to let n be the number of sides the regular polygon has. We're going to let a be the length of the apothem. We're going to let s be the length of the side length of our regular polygon, and we're going to let p represent the perimeter. Now you're going to see, at first, I'm going to kind of find in a sort of an unpolished form for the area of our regular polygon, which actually I prefer the unpolished form, and then I'll show you the polished up form of how we derive the area formula. Now we've been using the hexagon kind of as our foundation, as a kind of like our template. However, remember that regular polygons vary in side measure, or vary in number of sides, which means we need to derive an area formula such that it is dependent on the number of sides. So where we actually begin is in our diagram below with our regular hexagon as our template, we have an apothem drawn in and we have a side measure labeled. I'm going to draw in two additional segments. I'm going to draw in a circumradius from the center point to the endpoint chosen for our side there, and a second circumradius from that endpoint chosen for our side here. And what we find ourselves then with is we find ourselves with this highlighted triangle. Now, we know, we've studied this already, the area formula of the triangle is simply 1/2 base times height, right? That's kind of the foundation of all triangles. However, if we take a good look at our the measures given with our hexagon kind of be as our template, that triangle, we actually have values in terms of the regular polygon of the height and of the base. If we take a look, this is why it's important for us to know the length of the apothem, because the apothem is really the height of our triangle that's formed there. And the base of our triangle is the side length of our regular polygon, which means we can essentially transform the area of this triangle into terms that use these measures associated with the regular polygon. So it's 1/2, the base is s, and the apothem, or the height, is the apothem length. So if we think about that, we can actually calculate the area of that one triangle, knowing the apothem length and knowing the side measure of our regular polygon. So then how do we generalize this to actually find then the entire area of the given polygon? Well, if we draw in more circumradii, we see that we are actually going to be able to cut our regular polygon into the same number of triangles that the regular polygon, as the regular polygon sides. And as you can see, that if I were to compare the triangles formed, as it turns out, all those triangles are provably congruent, which means the areas of all of them are the same. So if we have said that n is to represent the number of sides of our regular polygon, n also represents the number of triangles that we can actually cut out of any given regular polygon. Now, combining this idea with the area of that given triangle, we come up then with the area of our regular polygon, which we find the area of our regular polygon is such that it is 1/2 the side length times the apothem times the number of sides n. And that right there is the raw form, kind of the unpolished form of our area of regular polygon. Now, you do notice that above in our text, I do mention that there is, we're going to let the perimeter represent this value of p. So where do we get that? Well, think about what's going on inside of our product there. 1/2 times the side length times the apothem times n. Well, with the commutative property of multiplication, we can kind of rearrange our terms of multiplication there, our factors, essentially finding the fact that we're taking at some point the side measure times the number of sides. Now think about that. If you took the side measure and multiplied by the number of sides, what do you really get? You really get the perimeter, which means we can alter this version to its polished form. So the area of our regular polygon is equal to 1/2 the perimeter times the apothem. And so there we have it. That's going to be our polished form. Now, I prefer the unpolished form when actually looking to find the area of a regular polygon, because I think of it as like a checklist. There's really 3 things I need. I need to know the measure of the side, the measure of the apothem, and I need to know how to count, right? I just need to know how to find how many sides my regular polygon has. And with those 3 things in play, then I can calculate my area. But the polished form we're going to see is going to be useful for us as we carry that out of this lesson into our next, when we look at the derivation of our circle area. So what we're going to do is, in the next several slides, we're just going to do some examples using our newly found area formula for the regular polygon. So before we get to our first example, though, I want to kind of give you a check-by-check list of things to do as you're approaching any given regular polygon. So how are we going to apply this to find the area? Well, step 1, they're going to hand us a regular polygon, and we're going to mark the center. From that center point, we're going to construct 2 segments. We're going to construct a circumradius, and we're going to construct an apothem, and that's going to form a right triangle for us. Then what we're going to do is use our prodigious knowledge of right triangles to find the values of our perimeter and the apothem. In our case, I like to find the side length and again count the number of sides, and then we're going to take those values and plug them into our area formula and arrive to our solution. So let's dive into our very first example of finding the area of a regular polygon. We're going to start with the area of a regular hexagon. Now, as it turns out, before we dive into this, here's just some food for thought. We really love 3 regular polygons. We love them all, but 3 of them really stand above, head and shoulders above the others. And the reason why is because there are 3 regular polygons that produce special triangles for us. Those 3 regular polygons are the triangle, the quadrilateral, and the regular hexagon. All 3 of those, if we dive into those, we're going to find ourselves with special right triangles, because from an equilateral triangle or the regular triangle, we can actually cut out a 3690. From the square or the regular quadrilateral, we can cut out the 4590, and with the hexagon, we are going to find ourselves cutting out another 3690 right triangle. And because of that, it's going to make finding our missing side measures and ratios much easier, because we know what the ratios of the 3 sides of our special right triangle are. So we're going to follow through with our checklist, and what I'm also going to show you is basically breaking down the scenario for every single regular polygon into a simple triangle. Okay, we can actually use a simple triangle in any case, no matter what side's given, to find the area of that regular polygon. So to follow through with our first step is we're going to mark the center of our regular hexagon here. We're then going to construct 2 segments. We're going to construct the apothem, which is perpendicular to our side there, and we're going to construct our circumradius. Now, we are going to let R represent the length of the circumradius, A is the length of our apothem, and S is the length of our side. Now, one thing to remember about the properties of the apothem is that it bisects the side, which means this length right here of that right triangle is 1/2 of our side length. Well, we are given the value of our apothem. So I'm going to go ahead and I can plug 12 in there. Now, with this information, we need to find the missing side measure, because if we think about the area formula of our regular polygon we just derived, again, I like the raw version, which is 1/2 S times A times N, the number of sides. So I think this is a checklist. Well, I can count the number of sides, check. I know there's 6 sides. I was given the apothem, that's 12, check. But do I have the side measure? Nope, I don't have that, which means our goal is to find the length of that side. So how do we go about doing this? Well, we need to know that there's actually one other additional piece of information we can find out about this triangle. And the additional piece of information we can find has to deal with this acute angle measure there, which I'm going to call alpha. As it turns out, if I were to construct every single circumradius and apothem within our regular hexagon here, what it does is it cuts our this regular hexagon up into 12 congruent triangles. In other words, I can actually calculate what this angle is. And the simplicity behind finding this angle measure alpha, is to think of it as one full rotation about the center of our regular polygon, and then dividing it by 2 times the number of sides. Because the circumradii, I cut it into n times the number of sides, but the apothem bisects those angles, and which means it really cuts it into 2n number of angles. So we can actually find the measure of this acute angle measure by simply taking 360, our one full rotation, divided by 2 times n, where n is the number of sides. So let's go ahead and calculate what that acute angle measure is. We have 6 sides, so we have 360 divided by 2 times 6, which is 12, which we're doing 360 divided by 12. That gives us a beautiful angle measure of 30 degrees. So this is why we love hexagons so much, because this triangle that was formed now with our apothem, half our side length, and the circumradius, we know this is really a 30, 60, 90 right triangle. And we can use that then to find out the missing measure of our side length. Because what I'm going to do is I'm going to take the apothem, which is now our long leg, and move to find what our short leg is by dividing by root 3. So the short leg, which is 1/2 S, is really equal to 12 divided by root 3. Now, what we find there is I can simplify the right-hand side. 12 divided by root 3 simplifies to 4 root 3. And then I can get my side length by multiplying both sides by 2. So the side measure is 8 root 3. So now that I have 8 root 3, I can change my story over here with my checklist. Check, check, check. I have everything I need. So let's go ahead and plug that in. So the area of our regular polygon is 1/2 our side measure, which is 8 root 3, times our apothem, which is 12, times the number of sides, which is 6. We can multiply all of our outside factors, 1/2, 8, 12, and 6. We get our value of 288, and that's all being multiplied to that square root of 3 still. And so there is the area of this regular hexagon. Now, to rewind and go back to the very beginning, what was it that really tied everything together? It was this simple triangle that we could actually cut out of every single polygon. Every single regular polygon can be divided, or can be cut out of this. We can cut out this simple triangle, which is the right triangle, such as the legs are the apothem. The other leg is 1/2 S, and the hypotenuse is the circumradius, which will let the R represent the circumradius. And we can actually calculate that angle alpha in every single case, because we're going to have the number of sides, and we simply take 360 divided by 2n, and that's going to give us our alpha. And then from there, we can either use our special right triangles if we are given one of those nice angles, or you're going to see in some cases we don't have those nice angles, which means we're going to use our trigonometry properties to find the missing measures we need. So let's move on to a second example, looking at finding again the area of a regular polygon. Now, the second example, it takes a little bit more work, and here's why. Because when we're given the circumradius and we think about our checklist about the area of a regular polygon, we need 3 things. We need 1/2 the side measure, the apothem measure, and how many sides. Now, do we know the number of sides? Check. Yeah, it's a pentagon. But do we know the apothem length? No. Do we know the side length? No. Which means we have to use the circumradius in 2 times to actually figure out what the apothem length is and the side length is of our regular pentagon here. So let's follow through with our pattern. We first then draw in where the center is, construct 2 segments, the apothem and the circumradius. We know the circumradius this time is a length of 3, but we need to find the apothem, and we need to find the side length, which right down here is 1/2 s. Well, we also can find out what our acute angle measure here is by simply doing our 360 divided by 2 times n, which in this case we have 360 divided by 2 times 5, because we have 5 sides, so 2 times 5, which is 10. We get then our angle measure there to be 36 degrees. So our acute angle measure, 36 degrees. I need to use then my hypotenuse, which is length of 3, to find our missing apothem and missing side measures. This is where SOHCAHTOA steps in, because even though our angle, or our angle 36 degrees, we don't have any nice ratios with that. We're going to use trigonometry. In other words, we're going to have to approximate this area, just because trigonometry is going to approximate some of the measures for us. So let's go after finding the missing length of the side first. So our side is our opposite side to our angle, and our hypotenuse, which is given, is our length of 3. So we have the sine of 36 degrees is equal to our 1/2 the side measure over 3. We can then use this to solve for our side measure. Sine of 36 turns into 0.5878, and that's equal still to that 1/2 s over 3. I'm going to multiply both sides by 3. I get then 1.7634, which is equal to then half of our side length, and then multiply both sides by 2, and I get my side length to be 3.5268. And the reason why I'm keeping so many decimal places is just for accuracy. I'll round my area at the very end. Now we're going to move on to find our missing apothem length. So we still have our right triangle there with our acute angle measure of 36. We still have that hypotenuse of 3, and the apothem length is the adjacent side, which means we can again set up our trigonometry to find our missing apothem length. This time we're going to use cosine. Cosine of our angle, 36 degrees, is equal to our apothem over our hypotenuse. We can then turn our cosine of 36 into its ratio, 0.8090, and that's apothem over 3. We can multiply both sides by 3, which then is going to give us our apothem length to be 2.4270. I don't really need that 0, but there we have it. We have both of the segment lengths we need. So now we go back to our checklist and say, hey, look, we've got our side length, we got our apothem, and we have everything we need because we know the number of sides. Now we can plug this in. So we're doing 1/2 times our side measure, which is 3.5268, times our apothem length, 2.4270, times the number of sides, which is 5, and now we can evaluate this. So we multiply all that through, and we get, I'm going to round to the nearest tenth, roughly 21.4 is the area of our regular polygon. And so there we have it. Couple different ways of actually finding the area of the regular polygon depending on what's given. If they're giving us a apothem, we can use it to find the side. If they give us the side measure, we can use it to find the apothem. But in this last tricky case, which is they're giving us the circumradius, we have to use that 2 calculations to find both the side length and the apothem to arrive to our solution. Now, to finish off the lesson, I want to kind of point you to a phenomenal resource known as Wolfram Alpha. You may not have used it, but essentially is a computational intelligence, essentially, that you can use to check your answers for your homework assignment on the 10.8 lesson here with the areas of regular polygons. So if you head over to Wolfram Alpha, what you're going to find is a little text box where you can type in what you want to tell Wolfram Alpha to do. Well, it has a built-in function called area. So if you see down below, I've got 2 examples of actually what you could type in to give the area then of that regular polygon. So the first one, I could type in area regular sixgon, which it says we're going to calculate the area of a regular hexagon with the apothem, that's our next word there, 12, which is apothem length of 12. And Wolfram Alpha will recognize that command, and it takes a little while, but it will process that, and it will tell you what the exact area is, if it's possible, and also give you the decimal approximation of the area. And so it works with really any any of the regular polygons we want. No, we're not just limited to integer values. We actually can go pretty higher with like our regular size, like 100 gon, 1,000 gon, things like that. So we type in area of a regular n gon, followed by what are we given? Is it the circumradius? Is it the apothem? Is it the side measure? Whatever it may be, followed by what that measure actually is, and you can use that to help check your answers for tonight's homework. So be sure to hop over, take a look at the 10.8 homework assignment. If you have any questions over finding the areas of regular polygons, please do not hesitate to ask me. I will get back to you via email. With that, be good and do good.